Hello everyone. In today's video session, we'll be learning about two important non-destructive testing methods, ultrasonic testing and eddy current testing. Non-destructive testing is a wide group of analysis techniques used in science and technology to evaluate the properties of a material, component or system, and also to find the defects in a component without causing damage. Because NDT does not permanently alter the component being inspected, it is a highly valuable technique that can save both money and time in product evaluation. The six most frequently used NDT methods are fluorescent particle test, magnetic particle inspection, ultrasonic inspection, radiography inspection, eddy current inspection, holographic inspection. We'll be discussing about ultrasonic testing, which is a family of non-destructive testing techniques based on the propagation of ultrasonic waves in the object or material tested. Ultrasonic testing uses high frequency sound waves. Before completely understanding what is ultrasonic testing, let us first understand what exactly is ultrasound. Ultrasound is sound waves with frequencies higher than the upper audible limit of human hearing. Ultrasound is not different from normal sound in its physical properties, except that humans cannot hear it. The frequency of ultrasound waves will be approximately from 20 kHz and above. Bats use a variety of ultrasounds for detecting obstacles. In non-destructive testing, ultrasound frequencies ranging from 2 MHz to 50 MHz are used to conduct examinations and make measurements. Ultrasonics is widely used in engineering applications such as flaw detection, dimensional measurements, material characterization. They are also used in medical field such as sonography and ultrasound scanning. Ultrasonic examinations can be conducted on a wide variety of material forms including castings, forgings, wells and composite materials. Let us now understand what exactly is the principle of sound and how it is going to propagate in the materials. Sound is produced by a vibrating body and travels in the form of a wave. Sound waves travel through materials by vibrating the particles that make up the material. Sound cannot travel in vacuum. Sound energy must have a medium and has to be transmitted or transferred from one particle to another. Let us understand the basics of velocity of sound. The velocity of a sound in a particular material will be always constant. It is the product of the density of the material and the elasticity of the material. The velocity will not change if frequency changes. If the frequency changes, it is only the wavelength will change and not the velocity. Example, the velocity in steel is 5960 meter per second, whereas in water it is 1470 meter per second, and in case of air it is 330 meter per second. So if the medium changes, the velocity will also changes. Let us now brainstorm about velocity of sound. What will be the velocity difference in steel compared with water? What if the frequency remains constant? In which material does the sound has the highest velocity? Is it the steel, water or air? What if the frequency remains constant? In which material does the sound has shortest wavelength? Is it once again the steel, water or air? The answers. Think for a second. In such cases, always the velocity difference in steel compared with water is 4 times. Always the velocity of sound in steel is 4 times larger than the velocity in water. And the steel will always have the highest velocity, and air, the velocity of sound is low. How do we answer this? Always remember this formula. Lambda is equal to V by F, where lambda is called as the wavelength, V is the velocity of sound, and F is the frequency. The higher the frequency, the smaller will be the wavelength. Let us now understand the principle of ultrasonic waves. Ultrasonic waves are similar to light waves. They can be reflected, refracted and focused. Reflection and refraction occurs when sound waves interact with interfaces of different acoustic properties. The most important component of ultrasonic testing is the transducer. An ultrasound transducer is also called as a probe, is a device that produces sound waves. The transducer also receives the echoes and sends them to the computer that uses them to create an image called as sonogram. Moreover, the essential element of ultrasound transducer is the piezoelectric crystal. This piezoelectric crystal converts the electrical energy into mechanical vibrations. The basic principle of an ultrasonic inspection of materials is the propagation of reflected sound waves. As an example, a cylindrical workpiece is shown in the animation. The longitudinal section of the cylinder shows the position of atoms. At the left end, a disc is positioned which is used to transmit and receive the sound waves. When the sound waves are produced, there will be a pushing and pulling forces which makes the atoms to move towards the free end of the cylinder. When the sound waves reach the free end, the sound waves are reflected and gets back to the disc, which will now act as a receiver. If a sound wave is generated at one end of the workpiece, it will travel through the material with its speed of sound. At the free end of the workpiece, the sound is reflected, which then travels back to the receiver. Ultrasonic testing of workpiece. The transmitter is also called as transducer or probe. At a place free from the defect, the ultrasound travels to the free end and back to the transmitter, producing an echo. When the transmitter is moved little downwards, the cavity reflects the part of the wave. This part is reflected to the transmitter at the earlier than the back wall echo. Further moving downwards, the cavity reflects the complete sound wave. This method of detecting the defect using ultrasound testing is also known as pulse echo mode. When the wave reaches to the back wall, the echo produced is called as back wall echo. If the sound wave is reflected from the cavity, this echo is called as defect echo. The transducer is connected to the monitor. In the monitor, the intensity is plotted in y-axis and the time in x-axis. When there is no defect, then there will be two signals in the monitor. The first one is called as the transmission pulse. The second one is called as backwall echo. If the sound wave is partially deflected by the cavity, then an additional echo can be seen, which is called as defect echo. If the sound waves is completely reflected by the defect, then there will be only defect echo and there will be no backwall echo. The schematic diagram of ultrasonic testing is seen on the screen. It basically consists of a transducer, a component to be tested, and a monitor. The transducer is connected to the monitor where the signals are recorded. By knowing the velocity of sound in the material as well as the time taken for producing an echo, the distance of the defect from the top surface can be determined using ultrasonic testing. Here, a couplant or a thick gel is applied on the surface of the material to be tested. This couplant will help to have a complete surface contact with the probe and the surface of the test piece. This is how a transducer will exactly look. You can see a cylindrical specimen having few defects and also a monitor having intensity plotted in the y-axis and time on the x-axis can be seen on the screen. Initially, there will be no echo in the monitor until a couplant or a thick gel is placed or applied on the surface. This couplant will increase the surface contact on the probe. Now you can see the backwall echo on the monitor. The gel is completely placed on the surface to get the echo from the surface. Using the velocity of sound in the material, one can find the distance of the defect from the top surface. The distance can be plotted in the software. If the probe is moving towards the defect area, there will be a defect echo which can be seen in the monitor, indicating the presence of crack. The distance of this crack can also be seen in the monitor. One can see that there is another echo which is generated on the monitor, indicating the presence of crack now. A double echo can be seen on the monitor due to reflection of the sound waves. The defect can be clearly observed now on the screen, and we can observe how an echo is formed when the sound waves are reflected from the defect. This is the basic principle of ultrasonic inspection, and this process has got many applications in industry. Let us now discuss the various advantages and disadvantages of ultrasonic inspection. This process can detect even a minute flaws. The shape, size and the orientation of the defect can be easily determined using this process. The method is faster compared to any other process. And the best part is the equipment is portable. The greater accuracy is found in this process compared to any other non-destructive inspection methods. Let us now see disadvantages. This process requires a skilled inspectors with extensive technical knowledge. The surface cleaning is most important in this process as the parts that are rough, very small, thin or non-homogeneous are very difficult to inspect. The components like cast iron and other coarse-grained materials are difficult to inspect due to low sound transmission and high signal noise. With these few disadvantages, this process is very much popular in the industries. Eddy current inspection is one of the largely used non-destructive testing process and has got many applications. Let us now study the basic principle and working of eddy current testing. Eddy current is one of the many electromagnetic testing methods used in NDT that makes use of electromagnetic induction to detect and characterize surface as well as subsurface flaws, especially in conductive materials. These currents were observed first in 1824. This testing is now widely used and well understood inspection technique for flaw detection as well as thickness and conductivity measurements. Let us understand what exactly is eddy current. Eddy currents are the loop of electrical current. They swirl around. They are induced in conductors by a alternating magnetic field. So what does it mean by alternative magnetic field and how these alternative magnetic fields are created? Alternative magnetic fields are produced when an alternating current is passed through an electrical coil. This coil is also called as inductor. When the AC current is passed through this coil, it generates the magnetic field and it is also known as primary magnetic field. This inductor is a device that keeps the current flowing through it a constant. Then how does a eddy current is produced? So when a conducting material is placed near the primary magnetic field, eddy current is formed in the conducting material. This is the basic principle of eddy current. Now let us understand how eddy currents are used to test or detect the cracks. Let us now understand how these eddy currents can be used to detect the cracks. When the eddy currents are induced in the conducting material, it forms another magnetic field which is called as secondary magnetic field. These secondary magnetic fields opposes the primary magnetic field. So indirectly it offers a load on the electric circuit. Due to this, there will be an increase in the current flow in the coil. When there is a defect, there will be a change in the current flow and thus the defect will be identified. Let us see that process. When this eddy current or the secondary magnetic field encounters a defect in the connecting material, then this defect will offer resistance to the flow of eddy current. Thus, there will be increase in self-induction or there will be reduction in current flow in the coil. This reduction in the current flow in the coil will be identified as the presence of defect. Eddy current has got wide number of applications because of its simplicity and methodology is easier to detect the cracks. The schematic diagram of eddy current inspection is shown in the figure. When a coil or a probe carrying an alternating current is brought near to the workpiece metal, the magnetic field of the coil will induce eddy currents in the workpiece surface. The magnitude and phase of the eddy currents will affect the loading of the coil. When the workpiece metal is defect free, the eddy currents will be uniform and consistent as shown in this figure. However, if there is some defect, then the eddy currents will be disturbed from their normal circular pattern. This will reduce the eddy current flow, thereby decreasing the loading on the coil and increasing its resistance. The resulting change in the phase and magnitude of the eddy currents is displayed on a monitor. This gives the operator the ability to identify the defect in the workpiece. The size of the defect can also be determined to a certain extent by using this process. Let us now discuss the various advantages and disadvantages of eddy current inspection. One of the major advantages of this method is that a variety of inspections and measurements can be performed, like defect detection, hardness, material thickness measurements, coating thickness measurements. Thus, this method has got a wide variety of applications. The test probe or the coil used in this process does not require any direct contact with the part to be inspected. This test is very sensitive to small cracks. Thus, it can detect the cracks at micron level. The equipment is portable and the accuracy is very high. Let us now discuss few disadvantages. This process is only suitable for conductive materials. A skilled operator is very much required during this process. This process requires an extensive surface cleaning or surface preparation. The depth of the penetration is limited. Thus, the cracks which are underlying below the surface is very difficult to detect. And one of the major disadvantages in this process is the cracks lying parallel to the current path cannot be detected. Thank you, my dear viewers. We will meet in our next session with some other non-destructive testing methods. Till then, have a nice day. Thank you.